Well, hey, let's pick up with some new content for Calculus 1. Today, I would like to talk with you about our new content for our last blob in this class. We're going to be talking about Chapter 5. Specifically, today we're going to be talking about Section 1. Chapter 5 is all about integration, and it starts with the fundamental method of integration, approximating area. We're going to be working on two major outcomes from this section. The first one, understand the need to approximate area using rectangles and write formulas for left and right areas. And then out of these themselves is approximate an area. And those areas are going to be given by functions and intervals. I would like to mention that I do have a rather complete set of Lightboard videos on these topics. And so if you happen to like my Lightboard videos more than these recorded lecture style videos, then by all means I would invite you to watch those. They don't perfectly follow my notes because I do not make these Lightboard videos to be consumed in conjunction with my notes necessarily at this time. Instead, they're intended for general consumption by the world and hopefully are useful to anybody in any Calculus 1 class, not just mine with my notes. So if these work better for you, then by all means, check them out. So I think they're pretty good. So preface. A preface to this section. Integration is the practice of accumulating change. How much water flowed through the did you walk? How much snow fell? In each of those statements, how much, how many, how much. We're asking about accumulation. Accumulation is the fundamental act that we're thinking about in the world of Chapter 3. Chapter 5, I don't know where I got 3 from. Chapter 5 is all about accumulation. Accumulators. So in each of these scenarios, there's water flowing, there's miles walking, there's snow falling, and in each of those instances, there is a rate of change. And we are being accumulated. So this is all about accumulation. And the purpose of this particular section 5.1 is to empower you to estimate net change given a rate of change. We're working on estimation. I would like to say that in addition to the approximation methods in this section 5.1, we are also going to learn how to integrate symbolically and exactly. And that content is in section 5.2 to 5.8. That is to say, the rest of this chapter is all about that. We have this one section on the estimation methods. And I think it's really important that we pay attention to the world of approximation, because in the world of integration, broadly speaking, the world of accumulation of change, there are two ways that we can compute that accumulated change. One, we can approximate it, and two, we can compute it exactly and symbolically. When possible, we will do exact and symbolic computations. But one thing to pay particular attention to is that exact and symbolic requires a functional form f of, say, t or f of x. I have to know what that function is in symbolic form. But a lot of the times out there in the world, we don't have the symbolic form for the functions that we're integrating. For example, a lot of the integration that our phones and cars do, that our government does in terms of computing the total amount of water that flows over a dam. Now, all of that, we don't have a symbolic function. Instead, what we have to do is we have to approximate, and that uses the techniques in this section, although they use much more sophisticated methods. So we should use this particular section as an attempt to give you the concepts of approximation of net change, and a springboard into taking more classes in the future to learn how this is done with much higher quality than what we're about to do. Okay? Let's turn the page. Okay, so So what we're going to do in this section is we're going to use rectangles to approximate area. There are other integration schemes that use that don't use rectangles, but use like trapezoids or a variety of other integration schemes, as well as varying the width of those things to approximate area. And we're going to focus our attention on uniform partition approximations using rectangles. I want to start by considering a scenario. So it's all about a rate of change and integrating that rate of change. So we're going to start with a rate of change, our velocity, right? The velocity is the rate at which position changes. Okay, and so I have just said, okay, well, let's let it be 2 times t, because we're going to start simple. We're always going to start simple. And I chose millimeters per minute because, hey, why not? I like units. So I'm going to draw a curve on the left-hand axis over here. And I'm going to draw it. It looks like I just drew, let me try again. It looks like I'm going to draw v of t equals t. But I'm drawing v of t equals 2t because I'm going to go 2, 4, 6, 8. This axis is labeled with millimeters per minute. And on the other axis, we are going to label it with 1 minute, 2, 3, 4. This is minutes. So it's not the same scale, but that's because I have the axes I have. Okay, so what I want to do is I want to calculate our total distance traveled over, say, the first 1, 2, 3, 4 minutes of our travel. So let's estimate the total distance traveled over first 4 minutes. Well, dealing with curvy things is generally difficult, and so what I'm going to do, and this is totally what our a variety of our various devices do in the real world, is I'm gonna say, okay, let's pretend I moved at constant rate and let's let that be determined by the left endpoint of a 1 minute interval. So over this interval right here, we believe that I was moving at 0 millimeters per minute times 1 minute equals 0 millimeters during that minute. And so my position changes not at all. Then for the next minute here, I'm going to have this area right here. And so I'm moving at 2 millimeters per minute, and I'm going to pretend that I'm moving at a constant rate for that next minute. So for the second minute, I was moving at 2 millimeters per minute for 1 minute, and I get 2 millimeters. So I moved 2 millimeters during that interval, and at the end of the second minute, I have, say, 2 millimeters. That's how far I've moved. I think I'm going to erase that line and simply say that's what I believe my position is at the end of that time. Let's do it for the third minute now, okay? So that's the time window from 2 to 3. I have that rectangle right there is of height 4. I'm going to erase the stuff inside the center here. The height is of height 4 millimeters per minute. And the width is 1 minute. And so during that minute here, I moved 4 millimeters. So at time t equals 3 minutes, I'm adding 4 millimeters, and my height is going to be up there. And then during the fourth minute, I've got a rectangle that looks like this. The height is 6 millimeters per minute. The width is 1 minute. And so during that time interval, I moved 1, 2, 3, 4, 5, 6 millimeters during that minute. And I estimate that I'm up there. So I could now try to like fill in a curve that matches that. And I get something like that. I have specifically those time intervals. And so my estimate, I traveled 0 plus 2 plus 4 plus 6 millimeters over those 4 minutes. That is to say, my net change in position is 12 millimeters. And it's an estimate because there is all this area here, 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 and here. All of that was unaccounted for. I didn't count it. And so the rectangles were off, and I got an underestimate. So I actually moved further than 12 millimeters in those 4 minutes. And that's because I'm estimating, I'm not computing it exactly. Another thing I want you to know is that over here I had a line, and over here I have something that looks like a parabola, and that is not a coincidence. So let's play that same game and do it with a parabola, t squared. So let's draw my rate of change. So let's do our same game, except this time let's use right endpoints to determine the height of my rectangles. Over this interval right here, here's the right endpoint, and here's the rectangle I get for that interval. Right, determined by the right endpoint. And I would add up the areas to give me my height after one interval. So the height over here is the cumulative sum of the rectangles over there. So I add up, say the area of the one on the left-hand side here is like 1. Let's say the area here is 3. I'm not using that specific function. And say this one was 6, then I would add up 1 plus 3 plus 6. Those are the areas. I'm adding those up, and I would have a total net change of 10. If we start with a quadratic, once we do this cumulative thing, we'll get something that's approximately cubic. Okay, so that was my high-level description of kind of what the game that we're going to be playing. And as we move to the next page, we're going to get more specific with it. So I have a final statement here. Hopefully this motivates you to want to learn approximation techniques, because we have devices that literally do this every day in our lives. And it's really cool. Moving pages on, we're going to use left or right sums with a given number of rectangles on a given interval and a given function to estimate net change or an interval. So let's make that really explicit here. I'm given a function in symbolic valuable form. Or I could be given a table of values that I have to go look up from. I'm given an interval. I'm given a left-right choice. There's also midpoints. I'm not going to cover midpoints in this video, but it's in the textbook, and I'm tell you where to find it. Okay, so those are the things that I'm given, and a number of intervals, of rectangles, or sub-intervals. So what we're going to do is we're going to draw a picture. I love starting with a picture. First thing I'm going to draw a picture, and I'm going to draw f, the rate of change, right? There's my f. Right, and we can use section 4.6 to do that, or a calculator, etc. We're going to draw the interval. I like using scripty I. How did I get on white? I don't want to be on white. Thank you very much. It's going to be the interval from A to B. We're going to discretize it, discretizing into discrete pieces or distinct sub-pieces. How many? You would have the number of rectangles. And so we're going to break this up into something like that. The fact that one of them happened to be on the root there was pure coincidence. 1, 2, 3, 4, 5, 6, 7, 8. Here in this one, we would say that number of rectangles is n equals 8. Our book likes to use capital N. I don't care. So we would have 8, n would be 8. I'm going to evaluate my function at each point, and I really like to build this table. If you haven't noticed, I really like building tables. And so in the left-hand side over here, these are the endpoints of the intervals. So on this, I'm going to label these as x0, x1, x2, x3, x4, x5, x6, 7, and 8. So there are a total of n intervals and n plus 1 endpoints. Okay? It's important that you know that that's true, that there's one more endpoint, and this is what they call a fence post problem in terms of these things being off by 1. So if you're counting horizontal slats in a fence versus the vertical fence posts in a fence, they're off by 1 from each other, unless you have a circle. And we're not integrating in circles. So I'm going to build my table of endpoints. I'm going to evaluate my function. This is the height of my function. So my height and my rate of change at my endpoints. I'm going to compute my areas. And so that's going to be to take each of these heights right here and multiply by the width of intervals. Okay, so that's the width of each of these small little pieces. How wide are those? We're going to call those delta x's or delta t or whatever your variable happens to be. Let's not get hung up on the name of the variable. So we're going to multiply each of those heights by the width of the intervals, and we're going to add them up. That's going to be our general process for doing these estimate the area under the curve problems. So what we're going to be doing is we're going to be choosing left or right. And let's say choose left on this one. And so my rectangles are going to look like this. Okay, so I have all these areas. We're going to compute them all. Nope, that's not one, sorry. Boop. It's possible that they have zero area. It's possible that they hang over. It's possible that they're deficient some. That's okay, right? So the height of the rectangle is determined by f of endpoint, and the width is delta x, which we're going to let be, I'm trying to write the word uniform. It's going to be uniform, and that's just to make the calculation simpler. It's actually computationally disadvantageous to take uniform mesh for all but the simplest functions. So take uniform width with a grain of salt. If you go on and do further work with numerical analysis and integration techniques and applied mathematics, you'll work with non-uniform partitions. And one of my videos, I'll point this out, one of my videos specifically talks about using non-uniform partition. And so I would like to draw your attention to that. So in the drawing that I have right here, these are all the same width. All of those are the same width. And I did that on the previous page. Also, these were all the same width. But there's no reason that we have to choose them all to be the same width. It just simplifies some formulas and simplifies some hand calculations. The computer doesn't care. And so, again, I would like to draw your attention to that video, approximating an integral with non-uniform partition. And I'm not going to cover that in this video. Okay, so that's a general process. I do need to tell you that I'm going to write down some formulas for what the right and left sums are, and in order to do those, we have to talk about what's called summation notation. And if you were going further in mathematics, particularly if you are in Calc 2 in the future, you have to know this stuff. So this summation notation right here, I would say that this is tremendously important. Particularly for people who are going to go on to take any subsequent math class. You probably will encounter summation notation, and it behooves you to internalize that notation at this point. So let's focus our attention on the summation notation right here. I have some pieces, and I have a nice video on this on the Lightboard section as well. So this thing right here, this is what we call the index, or the indexing variable. And this is the thing that that varies through the calculation. N is with the upper bound. M is the lower bound. And then AJ, this whole thing right here, are values we're adding up. In this particular notation right here, we don't say where you go get your AJs from. We're just saying there are AJs and you're going to go get them. And we would say A sub J, where the sub is short for subscript. So say A sub J, that's how we narrate that. And then this thing right here is a sigma, not sigmol, sigma is the name of the character, and it's a Greek capital S. So anytime you see somebody use that symbol as an E, you can laugh at them and just pronounce it as an S to be annoying to them. Because they're engaging in cultural appropriation. Anyways, for example, as far as this notation, this particular notation here, we might have a table of j's. We might have a table of j's and a sub j. So maybe j starts at 0, 1, 2, 3, 4, 5. And then this is like 1, -1, 2, -2, 3, -3. Let's go do a 6 and 7, 4, -4. They can be whatever you want. And we would say the sum from j equals 1 to 5 of a sub j is equal to, this is our first one of these, I'm going to take these j's from 1 to 5. Right? So those are my j's. They go from 1 to 5, including the 5. So 1 to 5. And I'm going to grab these values here and add them up. So we're going to add up those values. So the sum from j equals 1 to 5 of a sub j is equal to -1 plus 2 plus -2 plus 3 plus -3 is equal to -1. This one's kind of abstract in that it doesn't tell you what you're supposed to do. You just have to go get your a sub j's, wherever they came from. The next one that I have written right here is basically the same thing. And how does it differ? Here I have a formula to what to do with j. So I'm not going to have a table like I did up here. So up here I have this table, and I'm going to go grab my values from the table, right? Go look them up from the table. Here you generate the values yourself. And so I might have, for example, the sum from -2 to 3 of j to the negative, I better not do -1 because I've got the 0 problem. How about let's do j squared. Better put my j equals down there. All right, so this is going to be equal to -2 squared plus -1 squared plus 0 squared plus 1 squared plus 2 squared plus 3 squared, right? I've got my j's here. This is where my j is, right? It's inside of the thing I'm squaring, and it's ranging from -2 to 3, from -2 to 3. And we're doing it stepping by integers. There are ways to write sums so that I don't step by integers, but step by other values, fine. But it's a really compact way of writing a large number of summands all at once. So in this case right here, my f of j was equal to j squared. What do I do with j? I square it. As opposed to up here, where I'm like, what do I do with j? What do I do with j? I go look up the corresponding element from this table. So they're kind of different notations. In both cases, j is determining what the value is, but you take different actions. Now, this other notation right here is very similar to what we had before, right? I still have my index. It's also common to use I or j or k. Those are the common ones. It's very rare to use m or n or anything else. Sometimes you might use Greek characters, depending on the context. So in this one right here, we're still subscripting something. I've got the subscript onside my x's. And so here, I probably have a table of j's, say from like -2, -3, or -1, 0, 1, 2, 3, 4, 5, 6, 7, 8, whatever it happens to be. And then I have my corresponding x sub j's. Let's make those, say, be like -1/2, -1/4, 0, 1/4, 1/2, 3/4, 1, 5/4, 3/2, 7/4, and 2. And then I'm given some f. And so then I would have a third column in here, which would be my f of x sub j's, and I would apply f to my x sub j column, right? So it'd be like f of minus a half, f of 0, f of 3 halves. And so if I were to write the sum from, let's see here, let's do the sum from 3 to 6 of x sub j plus 2. And I'm going to use those parens explicitly to group both of those inside the sum. So I'm adding 2 to every term, not just 2 to the sum at the end. There is a difference. So that's not equal to the sum from 3 to 6 of x sub j plus 2. Because here the plus 2 is outside of the sum. Okay, so those are different. Let's replace my f of with something specific then. Let's make it be x sub j plus 2. It's still my f of x sub j. So f of x sub j is equal to x sub j plus 2. So it'd be like 3 halves, 7 quarters, 2 9/4, 5 halves, etc. So that sum here is equal to, I'm summing up which ones? I am summing up the ones from 3 to 5. I guess I better fill in those dots for those ones. I'll write them in red. 11/4, 3, 13/4. So this sum here, I'm summing up these 3 things, which came from these x values, which came from these indices. And so that would be 11/4 plus 3 plus 13/4, which would be equal to 24/4 plus 3, which is equal to 9. So summation notation is a powerful way to express a bunch of values that we're adding up all at once. And it's really cool. Okay. So we're going to be doing left and right sums. Let's draw a function. Let's try to draw the same thing in both places. That's why we usually choose like lines or something like that, because it's like really easy to draw a line the same every time. Are you willing to believe that those are both my same function? Cool. So let's focus our attention. Let's draw our interval. From A to B. I'm going to break it up, that interval, into n equal pieces. We're doing left sum. So when I draw my heights, that height was determined by x0, f of, right? That one there is determined by f of x1, all the way until I get to the last one here. That's determined by f of x5. And in the left sum, x sub n equals x6 for this particular thing equals b was not used. So I used this part of my table. I will add also that all of these heights are multiplied by delta x, which is the width of an interval. Subinterval, which is b minus a, the width of the total interval over n. Because I have an interval of width b minus a, and I'm breaking it into n pieces, and the width of an interval then is delta x equals b minus a over n. All right, okay, so that gives us our formula then for the left sum. So I'm going L sub n, L left, right? N tells me how many rectangles. What's missing from this is the function and the interval, but whatever. We'll never give this L sub n description formula without other context, telling you what function, what interval, and other various pieces. Okay, so what I'm going to do is I'm going to add up each of these values, but I stop and I omit that last one. All right, so I'm adding up f at x0, f at x1, f at xn minus 2, f at xn minus 1. That is to say, I get to write that I have the sum from j equals 0 to n minus 1. 0, n minus 1. Stopping. We're omitting that top one. We're omitting that top one, minus 1. What am I adding up? F at x sub j. And I'm multiplying all of those by delta x. So I've got the height, and I've got the width. And that approximates the area under this curve. Right? We're doing left sums. And so the area that I pick up is this area inside of here, including a little bit of overage in a few places. Okay, so that's my area. Now, I'm going to pull that delta x to the front because it's multiplied by every single one of these and it's the same. It doesn't depend on j. Does not depend on j, which means I get to pull it to the front. So I'm going to write L sub n as delta x times the sum from j equals 0 to n minus 1 of f of x sub j. That's what I do. Let's play that same game for the right. Let's break our interval from A to B into equal pieces. Let's do the same number, 6. I'm going to use right endpoints. And the area that I estimated then is this area here, including some overage there, and including some underage here. That value is, this area is equal to r sub n, the right sum. When I do that, I add up, I'm using this part of the table, because if you look at the right-hand side over here, that's where x sub n is at this end. And the height here is determined by x sub n, the height for the last one on this side is determined by x sub 1, and x sub 0 equals a was never used. So when I write down the formula for the approximation of the function f over the interval from a to b broken into n pieces using the right endpoint method, that's what this one little r sub n stands for. It's that whole thing. This is equal to the sum from what's my lowest value in terms of subscripts, 1. I'm going from 1 to n. The sum from j equals 1 to n, f of x sub j times delta x. And we're going to use that same trick to move the delta x out front, because delta x is constant with respect to j. And I have that that's the formula for the right sum. That is to say, an approximation for the net area under F between A and B using n rectangles and right endpoints. That's what R sub n is. It's an approximation for the net area under f of x between a and b using n rectangles and right endpoints. There are other schemes. In particular, on page 289, our book gives m sub n with a capital M. That's for midpoint. I'm not going to cover that in this video because of our truncated semester. But now we have the formulas. And we should do some examples and then call this video good. The internalization is really going to come from working problems. So let's first work with summation notation to identify pieces of the summation notation and how they fit together. All right, I think this is going to be quite instructive. Hopefully it is. So focusing our attention on the problem itself, let f of x equals the square root of x squared plus 1 and delta x equals 1/3. Sketch the graph of f and draw the left endpoint rectangles whose area is represented by the sum. All right, so we're going to need to draw a graph. Okay, no problem. There's my graph. Let's let that be x. This is going to be the height determined by f of x. Let's see here. So we need to draw the left endpoint rectangles whose area is represented by the sum. We have to have a few things in order to be able to do that, in order to be able to recognize the area. I need to know f. I need to know my interval, a to b. I need to know number of rectangles, n. And I need to know whether it's left or right. So, f was given. That's the square root of x squared plus 1. I need to know, let's focus on the number of rectangles next. How many rectangles? Well, let's look at the sum that I'm given from 0 to 5. Flipping back to the previous page, which one of these went from 0? Well, left did. Okay, so left went from 0 to n minus 1 and had a total of n pieces. So in this case, I'm going from 0 to 5, but 5 is equal to 6 minus 1, which means I have 6 rectangles. Delta x is 1/3 Okay, I see delta x is a third. We want to figure out our interval from a to b. The lowest place, the smallest x value at which we're going to be evaluating f. So let's work on the interval from a to b. We want to figure out that. With the smallest value at which we evaluate f in this sum is when I equals 0. And so that's, it's going to look like f of 1 plus 0 times delta x equals f of 1, which means that that lowest value is a equals 1. So I know what a is. A is 1. Cool. So next we need b. So I'm starting at a equals 1, and I'm going plus delta x 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 plus delta x, a total of 6 times. I'm going to be doing that action. I'm doing that plus delta x 6 times. Why 6 times? Because looking at the sum here, there are a total of 6 indices that I'm adding over. So I'm starting at 1 and adding plus delta x, a total of 5 times, because the first one I have is 1. So I think I have one too many of these, 5 times. I'm evaluating my function 6 times, but I have, I'm adding delta x 5 times, sorry. So my x values are going to be 1, 1 and a third, 1 and 2/3, 2, 2 and a third, 2 and 2/3. That's where j equals 0, j equals 1, j equals 2, j equals 3, 4, and 5. From 0 to 5. From 0 to 5. What did I just draw? I just drew a table of x's and j's. So my interval then is from 0 to 3. Remember, because I'm omitting the last one, that plus delta, another plus delta x would get me to 3, and then I'd be at 6, but we're omitting that because left. That's omitted because we're on doing left endpoints. So b is equal to 3. And then we're doing left because it started at 0. So from 1 to 3, I need the square root of my various x squared plus 1s. There we go. Delta x is a third. This height here is 1. Nope, that's root 2. Because square root of 1 squared plus 1 is 2. This is root 5. This is root 10. It's a square root function, and so it looks like that. That is the square root of x squared plus 1. And I've got left endpoints. And my area is this area here. All right, did we do what we needed to do? We sketched the graph of f. Yes. Draw left endpoint rectangles whose area is represented by the sum. Yes. The point of this exercise was to delve into the various pieces of this summation notation and how we can tell everything that we need to from it as long as we're given what f is. Okay? I'm not going to compute that sum right now. The point was the drawing. I will note as a concluding statement, this is an underestimate. Because I'm missing all of these pieces. I'm missing those pieces. Let's take a look at this function here. Why is L sub 100 bigger than R sub 100 for f of x equals x to the minus 2 on 3, 7? All right, so I think that we should start by drawing a picture. I love drawing pictures. I've got an interval from 3 to 7. My function x squared looks like, I want purple, 1 over x squared looks like this. I'll put in the other side too. Three to 7. So we're saying this is the left, this is the right. I think we should draw this picture twice. In fact, let's draw this picture side by side. Interval from 3 to 7. L sub n to R sub n. L sub n uses left endpoints. R sub n uses right endpoints. Take a look at what happened when we drew the left endpoints. All of these have extra area. All of those. All of those rectangles have too much area. Over here, all rectangles are too small. Right? They all have these gaps. Right? Like, let me shade the area that we're missing. We're missing that area, that area, that area, right? Those areas above, whereas over on this side over here, I have too much. What's the difference between these two things? Well, 1 over x squared equals x minus 2 is monotonic decreasing on 3, 7. And then because the left endpoints are always bigger than, so f of x sub j is always bigger than f of x sub j plus 1, right? And so we're always going to be overestimating. Using L sub n. On the other hand, if I had a function that looked like that and I do left endpoints, then now I'm too small, right? Now I'm missing a whole bunch of area in all of those. So L sub n isn't always an overestimate. L sub n is only an overestimate always for monotonic decreasing functions. So let's sum that up in some nice statement. For monotonic decreasing functions, right? That's a function that looks like that. It's always decreasing. This is on my interval from A to B. So it doesn't have to be decreasing everywhere, just on that interval. L sub n is an overestimate. For monotonic increasing functions. Go like that. R sub n is an overestimate. If the function is not monotonic, then we can't conclude without actually doing the comparison. Okay, so I think I'm on my second to last page here. This last one here, I know this video is getting a little long. This section has so much in it, and I would normally have 2 days on it, so I'm just going to ask you to excuse the long lecture. I will remind you that you can watch these videos slightly faster and skip around in them easily too. Let's calculate the approximation from 0 to 2, where I have the square root of 2 minus x. I love starting by drawing a picture. We are working on 0 to 2, so I don't need any of the stuff over there. I'm going to erase that also. So we are from 0 to 2. I need my function. When I put in 2, I get 0. So my height at 2 is 0. And when I put in 0, I get root 2. My function is a square root function that opens to the left like that. Okay, so that's my function. And we are being asked to do L sub 4. So that's the left endpoint method with 4 endpoints. This is going to be an overestimate. Okay. I really like developing a table. I'm going to put my x's and my f of x's. And I'm going to put my sub j's right there. The left has us work over the first 4 indices, 0, 1, 2, and 3. Our x values are 0, 1/2, 1, and 3/2, taken as 0 plus 1 times a half, 0 plus 2 times a half, and 0 plus 3 times a half. And this thing here is a, and then this part right here is j times delta x. My delta x equals a half. So let me put in my x sub j's, 0, 0.5, 1, 1.5. F of x sub j at those places. Well, okay, so I need the height of the function at those places. It's going to be root 2, square root of 3/2, square root of 1, square root of a half. L sub 4 is equal to the sum from j equals 0 to 3 of f of x sub j times delta x equals, I'm going to move that delta x out front and do it later. I'm going to write that as a half times root 2 plus root 3 over 2 plus root 1 plus root 1 half equals, I'm going to get out my calculator and do this. I'm going to go a half, and all I got to do is add up those other values over there. So I'm going to go square root of 2, square root of 2, 1.414 plus square root of 3 over 2, 1.225 plus 1 plus the square root of a half, 0.7071 equals a half of plus square root 1.5 plus 1 plus square root of 0.5 equals half times 4.34606 and some stuff after it. It's an irrational number times 0.5 is about 2.173. Not that bad. Okay, so let's review the steps then. I wrote down my x sub j's. Those are given by, I like using my graph to help me get those. I can also take my base point, my left endpoint 0, and just add as much delta x. How many steps do you have to take to get to that point? Being careful to omit the 4. The j equals 4. We're not including that. That'd be too many rectangles. Evaluate my function, add up those function values, and multiply by delta x. And we get our value. So let's do that one more time. Let's do the right endpoints. I wanted to include an example where we did both left and right endpoints for the same function. I still have my square root that's doing this. Oop. Make it do my entire stroke again. Okay. Oop. So my right rectangles are going to be that rectangle, that rectangle, that rectangle, that rectangle. So my table then consists of, here's my j's, x of j's, 1, 2, 3, and 4, because r sub 4 is equal to the sum from j equals 1 to 4 of f of x sub j times delta x. Need my x sub j's. They're going to be 0.5, 1, 1.5, and 2. That's a 0.5. There's that square root of 0. That's this one right here with height 0. So r sub 4 is equal to delta x times the sum of my stuff, which is equal to half times, I'm going to add up now these values that I found in this table. I'm going to go root 1.5 plus root 1 plus root 0.5 plus root 0 equals, okay, so square root of 1.5 plus square root of 1 plus square root of 0.5 plus the square root of 0 is 2.9318, blah, blah, blah. And so my estimated value is 1.466. And that's an underestimate. Okay, so one thing I'd like you to note is that in this table right here, I could have generated one table that had my j's from 0, 1, 2, 3, 4, my x sub j's being 0, 0.5, 1, 1.5, 2, my f of x sub j's being root 2, root 1.5, root 1, root 0.5, root 0. And then let me draw perhaps in like light purple, that section right there. If I work with that part of the table, I'm working with L sub n. And if I work with this part of the table here, then I'm working with R sub n. So if you need to generate both, you really only have to generate the table once, and then you just grab the appropriate section of it, right? Are you omitting the bottom row and just working with the top? Or are you omitting the top row and just working with the bottom as you work with R sub n? So that's a nice way to save a lot of time. Always make sure you omit one of the rows. Unless you're doing midpoints, in which case you have to be averaging things. Blah, blah, blah. All right, one more page, my friends. I know this is a long video. Maybe you took a break somewhere in the middle. That seems like a reasonable thing to do. I apologize for not breaking them into smaller pieces. It's simply too much effort for me to be doing that in the middle of the semester. Let's work with summation notation and rewrite some things as a sum and then calculate some sums. That's okay. I found a typo just now. All right. So what I want to do is I want to recognize this as a sum. I'm taking something to the third power in each of these. And where am I starting? -1. Where am I ending? 4. So I would write this is a sum as the sum from j equals -1 to 4, right? -1 to 4 of, what am I doing? I'm taking j and cubing it. Isn't that so nice? I think it's so nice. This next one here is, I did this one specifically because I think that we should rewrite this as like 3 to the 1 plus 3 to the 0 plus 3 to the minus 1 plus 3 to the minus 2 plus 3 to the minus 3. And when I write it like that, this can be written as the sum from j equals 1 to minus 3 of 3 to the j. And I don't really like having those out of order. So I think I'd rather write it as the sum from minus 3 to 1 of 3 to the j. So I can reverse those bounds, right? Boop, I can just flip them. And this is the proper one. And this is improper because the bounds are out of order. 2 more little problems for you. In this next one here, I have a typo. You can go ahead and fix that typo now by making that subscript be a k. That's fine. So what am I going to do? I'm going to take out my k's from 2. I'm going to, right, from 2 to 4, because k is going from 2 to 4. And then what am I doing to k? I'm taking it to the 4th power. I'm not actually going to run that arithmetic. I don't think that's important right now. Our last little ditty of the section, and there is just so much in this section. We're going to be taking j from 1 to 3, and I'm going to be taking 3 to the 1 plus 1 plus 3 to the 1 plus 2. Nope. Well, I mean, yes, but 2 plus 1 plus 3 to the 3 plus 1 equals 3 squared plus 3 cubed plus 3 to the 4th. And there are all sorts of things that you can do with this in terms of, like, there's no limitation in what you can do to the function right here. That can be literally anything. I think I want to make one more note. If you are still hanging on here, I want to thank you and tell you that the sum from I equals m to n of a sub I is equal to the sum from j equals m to n of a sub j equals the sum from k equals m to n of a sub j is equal to the sum from alpha equals m to n of a sub alpha. The name of the subscript doesn't matter. At all. Does not matter at all. There are a bunch of other things we could do with sums here. And unfortunately, I feel like our time does not allow us to really play with summation notation in the way that I want to this semester, because I want to like break apart sums and play like all sorts of those other games. And unfortunately, we lost 8 days of instruction. And one of those days is playing with summation notation. So if you were going on to a subsequent class after this, Calculus 2 probably, I think it would behoove you to spend time in section 5.1 working with summation notation, because it is something that's going to be with you for the rest of your mathematical career. Whether you become a mathematician or not, anytime you work with upper level mathematics, summations come up all the time. So I just want to say thank you so much for engaging with this long video. I know it's long, but it had to happen. We'll pick up next time with definite integration, and I want to say thank you so much. I'll talk to you later. Bye.